All right, guys, before we get started, are there any questions on any of the assignments so far? Okay. So number 8 on the first one, factoring 1. This one here. Now there is one on the first worksheet that doesn't factor, and we can check and see if this one is it. And to see if a quadratic is factorable, we can take the square root of b squared minus 4ac. If this comes out to an error in the 30xs, or a decimal, or with I, it doesn't work. Our value of b is negative 4, a is 1, and c is 24. And we can just do this off to the side. Yep. 4 squared minus 4 times 1 times 24 is domain error. So what that's telling us is that this number inside the radical is I, which is telling us that this is not factorable. Any other questions on the homework? For number 8 on the first one. Questions on either of the homework assignments? Now what we're looking at today are some special types of factors, more in how they, especially these first 3, factor in themselves. So if we look at this first one here, 4x squared minus 4x plus 1, we can still factor these the same way that we've been doing these the last few days. And we'll see that the result is something a little bit different. Because if we look at this here, the first thing we're going to look for is a greatest common factor. Is there a greatest common factor between our 4x squared, 4x, and 1? No. So we'll have our 2 sets of parentheses with 3 spaces. Then the next thing we're going to do is find the sign. Since the third term is positive, our signs are the same and they match the sign of the middle term, which is going to be minus and minus. Now at this point here, we need to find the factors of the first and third term. So our first term is 4x squared. So we will know, well, x squared's only factors are x and x. Now the factors of 4 are 1 and 4 or 2 and 2. Which one of these do we want to try first? 2 and 2. Now we also need to find the factors of the third term, factors of 1. Well, there's only one set of factors of 1, which are 1 and 1. Now at this point here, we can check and see if we got the correct terms, because 2x times 2x is still 4x squared. Our 1 times 1 would give us 1. So we're really checking the middle term. 2x times negative 1 would be negative 2x. Our negative 1 times 2x is negative 2x. And negative 2x minus 2x is negative 4x. Is that the middle term we wanted? Yeah. So it does work out that the factors of 4x squared minus 4x plus 1 is 2x minus 1 times 2x minus 1. Now there is another way that we could write this, as we can write this as 2x minus 1 squared. Since it is the same term, both factors are the exact same, we can merge it into 1 squared. That's why this one's a little bit unique, because, well, we could write it as 2x minus 1 times 2x minus 1, or we can just write it as 2x minus 1 squared. Either one of these will work as the correct answer. Questions on this here? Are you ready for the next one? Let's look at the next one here. 16b squared minus 40b plus 25. Is there a greatest common factor between these three terms? Because 2 will go into 16 and 40, but not 25. 5 does go into 40 and 25, but it doesn't go into 16. So there is not a greatest common factor for this here. So we'll have two sets of parentheses with three spaces. Now for our signs, since the third term is positive, the signs are the same and they match the sign of the middle term, which in our case would be minus and minus. Now we need to find the factors of the first and third term. So we're going to find the factors of 16b squared. But we know we'll have b and b. Now we just need to find the factors of 16. 1, 16, 2 and 8, 4 and 4. Which set of factors do we want to try first? 4 and 4. Now we need to find the factors of 25. Well, we do have 1 and 25, or 5 and 5. 5 and 5. And again, our next step is to check these here. So we'll do 4b times negative 5 is negative 20b. Then we can also do negative 5 times 4b, which is negative 20b. And negative 20b minus 20b is negative 40b. Is that the middle term we wanted? Yes. So negative 4b minus 5 times 4b minus 5 is the correct answer, or we can write it as 4b minus 5 squared. And just like the last one, these do have a special name. We call these perfect square trinomials.
Wait, I got a different answer.
4 times 8 would be 32.
Yeah.
2 and 8. Our net factors are 25.
Oh, well, I was.
So the factors,
okay, no.
yep, Smashville, but just a play on Nashville. Yeah. Questions on this here? We're going to do one more of these. 100x squared plus 180x plus 81. Two sets of parentheses with three spaces because, well, unfortunately, there is not a greatest common factor between these three terms. Our sign, since the third term is positive, our signs are the same and match the sign of the middle term. So we would have plus and plus. Now we need to find the factors of the first and third term. Well, 100x squared, we would have x and x for x squared. Now our factors of 100 are 1 and 100, 2 and 50, 4 and 25, 5 and 20, and 10 and 10. Which one do we want to try first? 10 and 10. Our third term is 81. So we'd have 1 and 81, 3 and 27, or 9 and 9. Which one of these do we want to try first? 9 and 9. And we can check this here. So the first one, when checking, we can do 10x times 9 is 90x. 9 times 10x is going to be positive 90x. And 90x plus 90x is 180x. Is that what we wanted? So these are our two factors, but we can also rewrite it as 10x plus 9 squared. Questions about these perfect square trinomials? Now, we've gone over these before, we've talked about them before, but I don't put a whole lot of emphasis on these because we could memorize or go over the properties of this, the fact that a squared plus 2ab plus b squared is equal to our a plus b squared. But it'll factor this way every single time. Or the fact that a squared minus 2ab plus b squared is equal to a minus b squared, and going through and remembering the pattern and how this works. Or we can just factor like we normally do. There's not a real, I don't see a real benefit to trying to memorize this here. Because the less things that we have to memorize or try to do with rote memorization, the better. And I think you'll have enough going on besides trying to memorize this pattern. Especially when our normal factoring techniques work just fine as they are. The next thing we're going to look at is this here, difference of perfect cube or difference of perfect squares. We'll do difference of perfect cubes later. Now the general form for this here is a squared minus b squared is equal to a plus b times a minus b. And if we have two terms being subtracted and they're both perfect squares, it's going to factor to this here. And one way we can check is if we look at this here, n squared, is n squared a perfect square? Well, yes, because what times itself is n squared? N and n, yes? Now we could rewrite this and say n squared. It really doesn't do anything, it's just n times n. But if we look at 25, what times itself is 25? And that would be 5. Now, part of the reason we write it this way, or I write it this way, is kind of just referring back to the general form. Because in the general form, our a is now being replaced with n, our b is being replaced with 5. So instead of having a plus b times a minus b, here we have n plus 5 times n minus 5. Because it's really our terms that are those perfect squares. So n squared was n, 25 is 5, n plus 5, n minus 5. Questions on how we did this here? Now we don't necessarily have to write it as parentheses n close parentheses squared minus parentheses 5 close parentheses squared. But if it does help, I would write it out. So let's look at this next one here. 16n squared minus 9. Is 16n squared a perfect square? Because n times n would give us n squared, yes? What times itself is 16? 4. So 4n squared is 16n squared. 4n times 4n is 16n squared. And what times itself is 9? So if we wanted to set it in the form of a squared minus b squared, it'd be 4n squared minus 3 squared. Then how would this factor? We'd have 4n plus 3 times 4n minus 3. That's it. Now if we want to check and make sure this works, we can. We don't. Because again, 4n and 4n, 4n times 4n is still going to be 16n squared. 3 times negative 3 is still negative 9, yes? Is there a middle term? No, there's not a term with just n, so it's understood to be 0, yes? And if we check this here, 4n times negative 3 would be negative 12n. Positive 3 times 4n is going to be plus 12n. Well, negative 12n plus 12n is 0n or just 0. It doesn't have a middle term. Questions on this here? Questions on anything we've done so far? Let's look at another one. 4m squared minus 25. Is 4m squared a perfect square? Because what times itself is 4? Well, 2. And the m squared is kind of somewhat self-explanatory. What times itself is m squared? M. What times itself is 25? 5. So this will factor 2. 2m plus 5 times 2m minus 5. And that's it. Questions on this here? Questions on anything we've done so far? Let's look at the next one here. We do have two things being subtracted, yes? This might be a difference of perfect squares. We'll look at the 9 first. What times itself is 9? 3, yes? Now the question is it possible to multiply something by itself and get a to the 4th? Because if we did a squared times a squared, yes? When we multiply like bases, we do what? We add the exponents, yes? Well, a squared times a squared would indeed be a to the 4th. Another way we can write it is a squared squared. Powers of powers, multiply. Now, in the previous ones, we didn't have a squared squared. We didn't have a squared term and then to the second power, yes? But it still works the same way. Because in the first spot, we're going to have, this time, a squared. Plus what? 3. And then we would have a squared minus 3. Well, for all case and purposes, realistically, that worked exactly as the previous one did, yes? The only real trick is the fact that instead of having a squared, we have a to the 4th. Still works the exact same. And really, this will work as long as the power of the a to whatever, or variable to whatever power is an even power. Because then I could do x to the 6 minus 9. Because we want to be able to write it as two things with to the second power. Powers of powers multiply, yes? Well, what times 2 is 6? 3, yes? So we could say that this is x to the 3rd squared. So this here would be x cubed plus 3 times x cubed minus 3. And it seems odd and it seems weird that this works. Well, if we actually distribute this back out, x cubed times x cubed, we multiply like bases, we add the exponents. X to the third times negative 3 would be negative 3x to the third. 3 times x to the third would be plus 3x to the third. And 3 times negative 3 is negative 9. So we have x to the 6 minus 9. It's interesting it works that way. But that's it. Now, unlike the last one, we do have squared terms inside the parentheses. A squared plus 3. There is no sum of perfect squares. There's not a formula for it. We don't factor it. It is and is not factorable at the same time. It is technically possible to factor it, but in order to factor it, we have to know the solutions. It ends up being irrational factors. So we don't consider that as part of one of the factors. But here we do have a possible difference of perfect squares, because a squared is still perfect square. Is 3 a perfect square? No. So that's it. That's the final answer. Questions on this here? Because this, again, you don't have to write this. This is above and beyond. Because if we went through and found the factors, or found the solutions for these here, it would be a plus I square root of 3 times a minus I square root of 3 for our a squared plus 3. And our other one's just going to be a plus the square root of 3, a minus square root of 3. Realistically, how we found those is we just set each of those factors equal to 0, solve for a, and then worked it back to get the factors. So it is, for the most part, it is possible to get the factors, but we have to know this. We have to find the solutions and work back to them, if it kind of makes sense. But here, in all cases of purpose, even college algebra, we say this is the answer. This is as far as it goes with factoring. We kind of get the hang of this here. Now we're going to do one more. I'm going to skip that one for now. I want to look at this one. X to the fourth minus 81. Well, as we just saw, x to the fourth is our x squared squared. Well, what times itself is 81? That would be 9, yes? So for our difference of perfect squares, we'd have what? X squared plus 9 and x squared minus 9. Questions on how we broke this down? We good with this here? Yes. Now, as we said on the previous one, x squared plus 9, we do not have any formula for the sum of two squares. So that's as far as it goes. The other one is a difference. X squared is a perfect square. Is 9 a perfect square? Well, yes. So really for the second one, what we're looking at is x squared minus 3 squared. It is a difference of perfect square also, yes? So technically, at this point here, it is not completely factored because the x squared plus 9 is, and our x squared minus 9 is also a difference of perfect squares, and it can be factored to x plus 3 times x minus 3. So we have to do it again. Now the reason we didn't have to do it on the previous one is, well, 3 wasn't a perfect square. So we didn't have a difference of perfect squares. And we were finished. Here, it is a difference of perfect squares, so this factors all the way down to x squared plus 9 times x plus 3 times x minus 3. Questions on this here? We're good with these so far. And interestingly enough, even with the higher powers, it still works that we could factor, because yeah, because I mean, this here, above and beyond, x to the fourth plus 8x squared plus 12. Because we can still factor this, it just works out 3 sets of parentheses, 3 sets of parentheses. Since the third term is positive, the signs are the same and they match the sign of the middle term. But our first term, x to the fourth, well, it does kind of have to line up with the middle. We end up getting x squared and x squared, because x squared times x squared would indeed be x to the fourth. And then we could go through the factors of 12, 6, and 2, and we can actually factor with this here. But that's above and beyond. We're not going to worry about that there. Now, the last thing we're going to talk about is this here. Now, this slide's not specifically written there, but they do. The next one, I believe, is x to the third plus 125. Yes? So that is our sum and difference of perfect cubes. Now, unfortunately, we're not going to get to the end of this packet today. We're going to finish this up tomorrow. But what we're going to look at is this here. Now, we didn't have time to really cover this before the break. We ran out of time in chapter 4 to cover factoring. I did include it as an extra assignment for those of you that wanted to watch the video and did. But we have this here. Now, sum and difference of perfect cubes, difference of two cubes, sum of two cubes, have specific patterns. And one of the specific patterns is with the signs. For sum, it is the same, opposite, always end on a positive note. For our negatives, our difference, same, opposite, always end this on a positive note. So for our sum, it's plus, minus, plus, same, opposite, positive note. Difference, same, so minus, opposite, plus, always ended on a positive note. And that helps us because now we're not having to memorize two set patterns for how the signs work. The values of A and B also have a respective pattern. Because if we look at A, our first term, well, it's cubed. If we take the cubed root of it, we just have A. First spot, it's A. Here we have A squared, A, and no A term. Really, it's A to the 0, but A to the 0 is 1. We're not going to have it listed. Our other one, our B, when we find its value, it goes here. Here we technically have B to the 0, but that is gone. The middle one's B to the first, and then we have B squared. So our first term, and the bigger one is going 2, 1, gone. The other term that's not there really 0, 1, 2. One of them's increasing in power. The other is decreasing in power. And it follows this pattern every single time in both cases. Does that make sense? Yes? All right. So, when we talk about the signs, same, opposite, always end on a positive note. Now, the first one we're going to look at, and well, the last example problem we're going to do today, is this one here. X cubed plus 125. Now, the first thing we can do in finding this is take the cubed root of x to the third. All right, guys, let's focus in here. And cubed root of 125. Now, out of these two here, taking the cubed root of x to the third is actually the easier out of the two, because it's just x, because the third power and the third root cancel each other out. Now, when we take the cubed root of 125, well, we can plug that into the calculator, and it'll tell us that it is 5. So for starters, it does tell us that this is a sum of two cubes, because x cubed and 125 are both cubes, and we're adding them together. So we do know what our values of our two spots, because then if we look in the general form, our a and b, a would be x, b would be 5. Now when we set this up, it is still two sets of parentheses. But because of the sum and difference of perfect cubes, first one's smaller, second one's bigger. Because in the first one, we're going to have one sign and two terms. The second one, we're going to have two signs and three terms. Personally, I'd nickname this the tractor trailer, because it looks like a semi in terms. And before we start filling in everything, I always start with the signs, because the signs are going to be the same, opposite always end on a positive note. So since we're talking about a sum, we started out with plus. Same would be plus. Opposite would be minus. Always end on a positive note would be plus. So for the sum or difference of perfect cubes, we're going to have plus, minus, plus. Questions on this here? Now our first term, our a's in the general form, for us here would be x. So in the first spot, and the smaller one is going to be x. In the bigger one, it decreases in power. The first one is going to be this first term squared. And the next spot, it's going to be that term to the first power, so just x to the first. And the last one, we don't write it. It's actually x to the 0. But it's not there, because it's just anything to the 0 power is 1. It's going to multiply with our other term and just be that term. Questions on this here? Our other term, our b in the general form is 5. So in our other spot in the first one is going to be 5. And the bigger one, next to the x squared, is technically 5 to the 0, which is 1. We don't write it. In the middle, it's 5 to the first. And in the last one, we have 5 squared. So for our x, that first term's going squared, first, gone. The other one's missing, first, squared. One of them's increasing in power, the other is decreasing. And this pattern works the same every single time, no matter what the numbers are. And the last thing we have to do is just simplify this down. Now, our first set of parentheses is just going to be x plus 5. It is exactly what it is. Now, we do need to do some simplifying in the second set. The first part here is this x squared. Well, x squared is just x squared. I believe so.
Is that the hodgepodge set?
No, I think that's the good set. Our middle one, x times 5, would be 5x. And lastly, 5 squared is 25. So our sum of two cubes works out to be x plus 5 times x squared minus 5x plus 25. And the interesting thing with this is that this quadratic part of the set of factors will never factor. It'll always have complex solutions. But that is where we're going to end it today.
What is this class?
Algebra